Now let us study the gradation in the halogen family. Halogen family is the elements in the 17th group of modern periodic table. These elements are fluorine, atomic number 9, fluorine, atomic number 17, bromine, atomic number 35, and iodine, atomic number 53. Their physical states are as follows. Fluorine is a faint yellow colored gas. Chlorine is a faint greenish colored gas. Bromine is a brown colored liquid, the only liquid non-metal at room temperature. Iodine is a purple or violet crystalline solid. In this way, they differ in their physical properties and their colors. Now, how do they differ in their atomic size? Electronic configuration of fluorine is 2,7. Fluorine is 2,8,7. Bromine is 2,8,18,7. Iodine 2,8,18,18,7. So, looking at the electronic configuration, we understand that fluorine has 2 cells, chlorine has 3 cells, bromine has 4 cells, and iodine has 5 cells. In this way, fluorine is the smallest atom, fluorine is bigger than fluorine, bromine is bigger than chlorine, iodine is bigger than bromine. So in this way, the atomic size goes on increasing from the top to bottom. Regarding the reactivity, fluorine is the most reactive halogen. In fact, it is the most reactive non-metal. Chlorine is less reactive than fluorine. Bromine is still less reactive than chlorine. Iodine is the least reactive. So, in this way, the reactivity of halogens goes on decreasing from top to bottom. Hello students, in the earlier part of this lesson, we studied how the chemical properties of filaments change in the group, that is from top to bottom, and how they change from left to right, that is in the period. Today one more property we are going to study, and that is a metallic character. As you can see, this list of elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, these elements are elements of second group. Now, among these, lithium and beryllium are metals. Boron is a metalloid, and these are non-metals. Metals, metalloids, non-metals. The next list, these elements belong to third period in the modern periodic table. So this is metal. Sodium is metal, magnesium is metal, aluminum is metal. So these are metals. Silicon is metalloid, and these are non-metals. Again, calcium, potassium, calcium, these are metals. So we see The elements in the left side of the modern periodic table, they are metals, whereas the elements in the right side of the periodic table are non-metals, and metalloids are in the middle part of the periodic table. So let us see what is a metallic character. So this is a sodium atom. Atomic number of sodium is 11. Its electronic configuration is 2A1. Means that here the first cell, K cell, has 2 electrons. L cell has 8 electrons. 1, 2, 3, 4, 5, 6, and M cell has 1 electron. So in this way, metals have either 1 electron, 2 electrons, or 3 electrons in its outermost cell, that is valence cell. Now, because of less number of valence electrons in the outermost cell, the effective nuclear charge, that is exerting force of attraction on the electrons, is less. Means these valence electrons are filled with the less force of attraction by the effective nuclear charge, and therefore these electrons the metal can lose easily, so that the penultimate orbit, last second orbit, becomes the outermost orbit, and that orbit is complete. So the metals do this to become stable, to attain the electronic configuration of nearest inert gas. Magnesium, let us take another example. Magnesium has 2 electrons in the outermost cell. So in order to become stable, magnesium will lose 2 electrons, and it will become the configuration of nearest inert gas, that is a neon. Aluminium has 3 valence electrons, so it will lose 3 valence electrons and will become the electronic configuration of neon. So in this way, metals have a tendency to lose the valence electrons and form positively charged ions called cations. So this property is called metallic character, or it is also called electropositivity. Electropositivity or metallic character, it is a property of losing the electrons and forming positively charged ions called cations. Now let us see how electropositivity change in the period and in the group. These elements belong to third period in the modern periodic table. These elements belong to the first group, alkali metals, in the modern periodic table. Now, from sodium, as we know, sodium has only one valence electron, so it can lose the electron very easily and form sodium ion. Magnesium has two valence electrons. The size of magnesium atom is slightly less than sodium, so it cannot lose these two electrons as easily as sodium does. So magnesium is slightly less metallic than sodium. Aluminium has three valence electrons. The size of aluminium atom is slightly less than magnesium. So aluminium loses three electrons, but it does not lose electrons as easily as sodium or magnesium. So aluminium is a less metallic or less electropositive. So as we can see, sodium is most metallic, most electropositive. Magnesium is a little less metallic. Aluminium is still less metallic. We know silicon is a metalloid, shows properties of metals as well as non-metal. So we see, as we go from left to right, that is in the period, the metallic character goes on decreasing. So sodium is the most sodium is the most metallic element, most electropositive element, whereas chlorine is the least metallic element or least electropositive element. Now let us see how metallic character changes in the vertical column, that is group. So lithium, sodium, potassium, rubidium, cesium, all of them are alkali metals. They have one electron in the valence cell, outermost cell. So all of them are going to lose electron and forming corresponding cations. But if we see, lithium has two cells and the second cell has one electron. So it loses this one electron and becomes stable. Sodium has three cells. The third cell has one electron. So it loses this electron from third cell, it becomes stable. Potassium has 4 cells. The next element, rubidium, has 5 cells. Cesium has 6 cells. So as we go from top to bottom, the number of electrons in the outermost cell is same. That is 1. But number of cells increase. Atomic radius or size of atom increases. So as the distance between the center of atom to the outermost cell increase, the electrons are held with the lesser force of attraction by the effective nuclear charge, and bigger the atom, it is easier to lose electron for the element, and the more will be the metallic character. So in this way, all these are metal, but the metallic character goes on increasing from top to bottom. This is because as we go from top to bottom, the new cells are successively added. The distance between the center of atom to valence cell, in other words radius of atom, increase. The effective nuclear charge exerting force of attraction on the electron decrease, the electrons can be easily lost, and because of this the metallic character in the group increases. So in the group, lithium is least metallic, sodium is more metallic, potassium is still more metallic, rubidium is again more metallic. So metallic character goes on increasing. So in short, how the metallic character change in the periodic table? It decreases from left to right in the period, and it increases in the group from top to bottom. Now let us study what is a non-metallic character or electronegativity. How does it change in the modern periodic table? So these are the elements in the third period of modern periodic table. Among them, these are non-metals. This is metalloid. These are metals. We will take three non-metals: phosphorus, sulfur, and fluorine. Phosphorus, sulfur, and fluorine. So if you look at these figures, you will find all of them have three cells: K cell, L cell, M cell. K, L, M. K, L, M. All of them have three cells. But the number of valence electrons in them is not same. As we go from left to right, the number of valence electrons is increasing. Phosphorus has 5 valence electrons, 1, 2, 3, 4, 5. Sulfur has 6 valence electrons, 1, 2, 3, 4, 5, 6. Fluorine has 7 valence electrons. As we have studied in the earlier part of this lesson, as we go from left to right, the atomic size decreases. Radius of atom decrease. And the electrons, valence electrons, are pulled with more force of attraction by the effective nuclear charge. And these electrons, valence electrons, they cannot be lost easily. So non-metals do not lose electrons, but in order to become stable, they gain electron, they accept electron. For example, here phosphorus, instead of losing 5 electrons, it gains 3 electrons and it becomes a phosphide ion, P minus 3. It means phosphorus plus 3 electrons, it becomes phosphide ion. It becomes stable. Sulfur has 6 electrons, it needs 2 electrons, so it accepts 2 electrons. Sulfur plus 2 electrons, it becomes sulfide ion. Chlorine plus 1 electron becomes chloride ion. So in this way, metals accept non-metals accept electron and they form negatively charged ions or anions. This property is called non-metallic character or electronegativity. So non-metals are electronegative. They have tendency of accepting electrons and forming negatively charged ions called anions. Let us see how this electronegativity change from left to right. In these examples, phosphorus needs 3 electrons, Sulfur needs 2 electrons. Fluorine needs 1 electron. Now the ease of accepting electrons, if we compare, chlorine needs only 1 electron. It accepts electron energetic most easily. So chlorine is a most electronegative, most non-metallic. Sulfur needs 2 electrons to become stable, like argon. So it accepts 2 electrons, becomes stable. But accepting 2 electrons is not as easy as accepting 1 electron. Therefore, sulfur is a little less non-metallic than chlorine. A little less non-metallic, electronegative than chlorine. The same way, if we go to right, phosphorus needs 3 electrons to become stable. It accepts the electrons and becomes phosphide ion, almost like argon. But accepting 3 electrons is not as easy as accepting 2 electrons or 1 electron, and therefore phosphorus is less non-metallic than sulfur. So here we see, when we go from, or in this, if we compare, which is the most non-metallic, chlorine. Sulfur is little less non-metallic. Phosphorus is still little less non-metallic. Like this, if we go, the element previous to phosphorus is silicon, is a metal, right? Then before silicon is aluminium, it's a metal, so it is still less non-metallic. So we see the non-metallic character is decreasing from right to left. Or in an opposite way, we can say the non-metallic character goes on increasing from left to right. Repeat, the non-metallic character or electronegativity goes on increasing from left to right. The most electronegative element is chlorine in this period, whereas the first element, sodium, is the least non-metallic or least electronegative. So in this way, the electronegativity or metallic, non-metallic character goes on increasing from left to right. Now, how non-metallic character change in the group? Fluorine is the smallest atom, has only 2 cells. Fluorine has 3 cells. It is bigger than fluorine. Bromine is still bigger. Iodine is the biggest atom. So, among them, fluorine accepts electron most easily. Fluorine cannot accept electron as easily as fluorine. Bromine cannot accept electron as easily as fluorine, and so on. And in this way, the non-metallic character goes on decreasing from top to bottom. Fluorine is the most electronegative halogen. In fact, it is the most electronegative non-metal in the periodic table. So, the electronegativity goes on decreasing from top to bottom. Now look at these elements: beryllium, magnesium, calcium, strontium, and barium. These are alkaline earth metals. belonging to the second period in the modern periodic table. When alkaline earth metals react with the water, they form their corresponding hydroxides, and in this reaction hydrogen gas is released. We can write general equation of this reaction. Suppose alkaline earth metal is the given metal. When it reacts with water, it forms hydroxide of alkaline earth metal. Alkaline earth metal, it's a hydroxide plus hydrogen gas is given. When alkaline earth metals react with water, they form their corresponding hydroxides of alkaline earth metal, and hydrogen gas is evolved in this reaction. Now let us see how the reactivity differs in the alkaline earth metals. Beryllium does not react with water. Magnesium, it does not react with cold water, but when it reacts with hot water, it forms magnesium hydroxide and hydrogen gas is given. So this reaction is Mg plus H2O gives MgOH2 plus H2. So this will be balanced equation. Mg plus 2H2O gives MgOH plus H2. So magnesium reacts with hot water. Calcium is more reactive. So calcium can react with water to form calcium hydroxide and hydrogen. Strontium, it reacts with cold water to form strontium hydroxide and hydrogen gas. Barium reacts with cold water to form barium hydroxide and hydrogen gases. So here we see the reactivity with water goes on increasing from top to bottom. This does not react with water. This reacts with hot water. This reacts with cold water. This to also react with cold water. But strontium reacts more vigorously with water. Barium still more reactive. So in this way, the reactivity of alkaline earth metals with water goes on increasing from